So here we are, two generations of granny charger electronics. And this has been quite a fun project to work on because it's such a nice like engineering optimization challenge. So as you know, the granny charger is my project to incorporate all the electronics for charging your car. That's the EVSE or electric vehicle supply equipment into the actual handle of the J7072 connector, so that you don't have this grinding charger, which is essentially just a cable, but there's like this box, which is quite heavy and big, right next to the Shuko connector. Now, the previous electronics were these electronics, and as you might be able to tell, there's some discoloration there. Doesn't look quite right. That is because it actually failed. Not very spectacularly, but it did fail, and I will talk about that soon. During the design process, I found out that the amount of board space that I needed, and you can see it is very, very packed on this board. Like, there is no room, discounting this bindi bit from between. Essentially, the relays goes directly onto the transformer, goes directly into voltage regulators. Capacitors have basically no room left. It's all packed in. And then there's the current sensor itself. So I was a bit stumped, like, how can I make this smaller? Because the connector, if you look at the connector side on, and I will show that in a minute, there is not enough room for this length of PCB. So the reason this PCB goes in twin is because it actually has to bend like that to fit into the handle. And yeah, PCBs don't do that. You have flex PCBs, but that's so expensive, especially in one-offs, just to test something out. So did it this way and had a lot of wires just connecting everything over. And I didn't really think about the wires. I just wanted to make a working prototype, and it worked, but this is very inconvenient. So there's even another capacitor on the bottom. So how do you optimize something like this? Well, there are multiple strategies I took. So I already spoke about the transformer. So this is literally the smallest transformer I can get from various component distributors. It's a 0.35 watt dual 12 volts. I need the galvanic separation because this entire circuit is ground referenced. So the 0 volts is actually like a protective earth lead that goes into there. And if this entire circuit, if this were a non-isolated switching mode power supply, which actually would be a lot smaller and a lot more convenient for this application, then there would have to be some return current over ground, and that will trip your GFCI. So that's not an option. It had to be isolated. So this is a must, as are the relays. These are literally the smallest 16 amp relays that are latching. And the latching is important because this transformer cannot produce enough power to drive these relays continuously. And also these relays, if I would have to drive them continuously, would get a little bit warm. I don't like that. I don't like things warming up. It just leads to like cyclic damage. So what other options do I have to optimize? Well, obviously here, these capacitors, they are very big. And the only thing they are doing is storing the energy to operate the relays. They're not used for the electronics very much because the electronics is basically just a microcontroller and an op-amp. Those only use about 1 milliamp altogether. So it's almost nothing. And they use that 5 volts, so with an SMPS to step that down, there's like no power use from this transformer. So I should be able to reduce these capacitors, and the size of these capacitors was based on the datasheet values of the amount of charge you need to reliably switch two of these relays. So what I'm doing now is I looked over the J7072 spec, and it is not necessary to simultaneously switch these two relays. So if I can switch them one cycle apart, I only need half the capacity. So that's already one of these big capacitors removed. Awesome. I'm actually very much inside the safety margin. They can be switched apart as far as you like, as long as you don't say that the power is okay and that the car can start charging. So apparently there's no limitations here. Second thing I can optimize, well, these voltage regulators here, yeah, that's not very space efficient here at the top, so I replaced those with the SMD versions. It's less space efficient on the board itself, but everything is smaller, and I will get into that, why that's important later. Now then, still there is this. And this big capacitor is to buffer the plus 12 volts, which then gets down converted into 5 volts into these capacitors. But wait a second, if I am using this to store energy to then put into here to then operate the relays, then this is all double. So I can get rid of these completely. And the reason for that is, at lower voltages, capacitors get larger for the same amount of stored joules. So this capacitor is a 25 volt 1000 microfarad capacitor, and like obviously it's only slightly smaller than this 2200 microfarad 6.3 volts, even though at 25 volts that's 25 squared divided by 6.3 squared, which is like a ridiculous difference in energy storage density. So yeah, this I mean there's some reliability stuff as well. So this is a 125 and this is a 105 degree capacitor, so there's some difference there, but in general it's better to store energy at a higher voltage. So that's exactly what I did, and with the lesser requirements on total energy stored, I was able to reduce it all to this basically. So these two capacitors are the high voltage storage. They are both 100 microfarads instead of 1000, and this is a 470 microfarad at 6.3 volts for the 5 volt stuff and for the relays. And altogether, these communicate capacity through each other via this DC to DC converter, which is a high efficiency one and also quite high current. And by switching at the right moment, the AC line, the reason we have to do all this buffering is because it does not continuously give us power. It gives us intermittent power 100 times every second. So if you time it right, you can get quite a lot of power. This is on average 0.35 watts, but on the peak it is about square root times 0.35, so it's like 0.5 watts. That's almost enough to drive these relays. We only need a tiny bit more. So yeah, this is like awesome to do this kind of optimization, to go from that amount of capacitors to that amount and still have plenty. Because obviously this will all get warm at some point. The grinding charger will be operated in the sun for hundreds of hours, thousands of hours. So these capacitors will degrade, and I made it so they are about 1.5, 1.6 times the necessary capacity. And so over time, this grinding charger will not start failing because it cannot operate the relays. So yeah, I mean, the capacitor thing, that's an awesome optimization thing. Another way to reduce the size is to remove this transformer. This was a current transformer that I used for GFCI. And the J7072, the abridged version, says that you need a GFCI on the charger, on the EVSE. And that is very annoying because GFCIs are a bit hard to implement. And they're not just blocks that you can drop in. Well, they are, but they're very big. It won't fit, so you have to do it with your own current transformer and some software. However, digging deeper into it, the GFCI is only necessary if you don't have a selective GFCI in your house. And as it stands, in the entire Schuko area, it is mandatory by code to have a GFCI installed in your house and have a selective GFCI. These days you even need, I think it's called a Type B GFCI, so it's a fast, lower current version. So this GFCI would actually not do anything, it will only interfere. So I can leave it out legally, which is awesome. So I did that. The grinding charger will carry a warning with it not to use it if there is no external GFCI. Now lastly, there is the programming port. So it used to be here, and this was just a horrible placement. Grinding charger electronics are installed like that into the shell of the connector, and being able to plug in the programmer to change the program is pretty important in the prototyping phase. And you would say, well, this looks pretty slick. And indeed it does. It's now a single PCB and it fits perfectly inside. There is no need to bend it anymore. So line input goes in here, line neutral and ground. The outputs of those, the line and neutral, they go down the side or down the bottom to the connector. So there are still a couple of wires running parallel to the board. But otherwise, the CP, PP, and the switch, they're all here. The LED is here. So there's much less wiring going on. Everything's just integrated on the PCB. Now, of course, I thought, well, nice. I've made an optimized design. Everything's good. I can just build this in, and I did. And of course, I didn't check for additional requirements. So on this board, basically what I made was a grinding charger that would work and not much else. This board is an optimization of the previous board, but I am still missing features. Most important one is the contactor welding requirements. So what you have to do in J7072 is to check whether your contactors have welded. So relays, when they are closed, they can weld together if there's a lot of current going through it, or if there's like arcing. Eventually they can stick together, will never come apart again. And that means there will be 230 volts on your connector all the time. When that happens, the thing should refuse to do anything. And unfortunately, in this design, there is no such measurement of whether the contactors are working correctly or not. So that still has to be added. And the second is, of course, a contactor open detection. So when the grinding charger is turned on and the contactors turn on, you have to check whether there's actually 230 volts on the other side to signal to the car that it should start working. And yeah, both of those still have to be implemented. So this is not yet a J7072 technically compliant grinding charger. There's one more revision before I start selling this. That being said, I am sending out samples to two people who were willing to test this on different cars. One on a Peugeot Ion and one on a Renault Zoe. This is all inside of here, and let me just magically open it up for you. Oh, that magic really hits the spot. Anyway, this is what it looks like inside now, and you can see that this the moving of capacitors from top to bottom was kind of necessary to make it fit the space. And yeah, the board, it just fits so nicely. It is awesome. There are a couple of differences since the last time. So the whole idea of this grinding charger, these connectors are not watertight at all. There will be water, there will be moisture and condensation inside. So this board has to be coated in the ends. And my plan is to have them potted in. So to have like the connector when I'm selling these, have the connector with the board in, conformally coat everything in one side, and then have the other side come off. and that way I can still reprogram them if necessary, and make safety changes, and maybe even like rework things if the switch breaks. But otherwise the thing will be safe from moisture. Obviously in the previous and this version I'm not doing that. The failure mode of the last one was here, and this was kind of obvious. I knew this was going to happen because you can already see here. Let me just zoom in. You can see that this thick wire that is connected to a very thin PCB. The PCB is under quite some stress, and on the previous board this eventually led to failure of the board and a short circuit, and that tripped a breaker. So this is kind of unacceptable. In the end, this will have to be, I think it will have to be a thicker board, honestly. This board is just, it's a 0.6mm f44 board. I think I'm going to go to 1.2, which will have something like 3 or 3.5 times the bending stiffness, so we'll be able to cope with these wires. In final version, I think the safest way will be to add a sheath board, or actually have a second board that runs the entire length and makes the power come out at this side. I think that's even better. So something like that will be implemented on the next revision, because yeah, this whole wire mess, it's still a mess. These wires, they're folded up because they were slightly too long and I didn't feel like changing them. But this can be just much neater still. Now, of course, the big new feature in this version is the fact that it is a programmable granny charger. So what does programmable mean in this sense? Well, of course, you can literally program it. There's a programming header inside, but that's not what I mean. You can set the current every time you charge. When you plug it in, the LED will flash a couple of times and that will show you something. So when you plug it in and within 3 seconds you press the button on top, you see that it flashes once, twice, 3 times, 4 times, 5 times, and 6 times. And this is setup mode, so whenever the granny charger is not plugged into the car, and if it's just on in the first couple of seconds, you are able to set the current in increments of 2 amps starting at 6 amps. This is the J7072 standard. You cannot go lower than 6 amps, and in this case it doesn't go higher than 16 amps. So 6 amps plus 5 times 2 amps is 16 amps. So that's how you come to 1 to 6 flashes. There's 5 in between. As you can see, if I press it now, it's been plugged in for longer. Now it is actually just in the operational mode. You cannot set the current anymore. You can only do that in the first few seconds if it is not plugged into the car. If you plug it into the car immediately, it will use the current setting that you set last time. So it will remember current settings over restart cycles, reboot cycles. And yeah, that is a very, very handy feature that I will be using a lot. So yeah, that's it pretty much for the granny charger update. I would show you the granny charger working, but I've already done that, so that's a bit superfluous. We'll only extend the runtime of the video. As with most of these electronics that I'm showing you, including, for instance, the next video maybe, that will be this board. These are just like technical intro videos. They're a bit dry and a bit dull. When I completely finish the granny charger to the actual like sellable state, as well as the other electronics, I will show like an overview video with everything working and lots of application examples and that kind of stuff. But for now, it's just like a technical thing to show you how I did things. And I really like the engineering aspect of these boards. So I hope you enjoyed regardless, and see you in the next video.